Lesson: Logic-based knowledge representation. Logic-based knowledge representation is a foundational aspect of artificial intelligence, offering a structured approach to encoding information about the world in a way that allows machines to process and utilize this information effectively. It leverages formal logic systems to ensure that knowledge is represented in a manner that is both interpretable by machines and manipulable to derive new insights or make decisions. One core advantage of logic-based representation is its ability to facilitate reasoning, allowing systems to infer new knowledge from existing data through logical deductions. At the heart of logic-based knowledge representation is the use of symbolic logic, primarily propositional and predicate logic. These logical frameworks provide a precise syntax and semantics for representing complex information. Propositional logic involves simple statements and their truth values, while predicate logic, an extension of propositional logic, includes quantifiers and predicates, offering a richer language to express more nuanced information. Predicate logic is particularly useful in AI because it allows for the representation of objects, their properties, and the relationships between them. A practical application of logic-based knowledge representation can be seen in expert systems. These systems use a set of rules and facts encoded in a knowledge base to emulate the decision-making abilities of a human expert. MySyn, an early expert system for medical diagnosis, used hundreds of if-then rules to diagnose bacterial infections and recommend treatments. The system's logic-based framework allowed it to reason about symptoms and suggest appropriate antibiotics, demonstrating the power of logic-based representation in real-world scenarios. One of the most significant challenges in implementing logic-based knowledge systems is ensuring the consistency and completeness of the knowledge base. Inconsistent or incomplete information can lead to incorrect inferences, undermining the system's reliability. To address this challenge, professionals can use automated reasoning tools such as At solvers and theorem provers. These tools can automatically verify the consistency of a set of logical statements or find models that satisfy a given set of propositions. For example, the Z3 solver from Microsoft Research is a high-performance theorem prover used in various applications, including verification, optimization, and analysis. Another key aspect of logic-based knowledge representation is the development of ontologies, which are formal representations of a set of concepts within a domain and the relationships between those concepts. Ontologies enable shared understanding and interoperability between systems, making them essential for areas such as the semantic web. OWL is a standard for expressing complex ontologies and is built on logic-based foundations. OWL facilitates the creation of detailed ontologies that can be processed by machines to perform tasks such as data integration or intelligent search. A practical framework for developing ontologies is the NEON methodology, which provides guidelines and tools for ontology engineering. The NEON toolkit supports the entire lifecycle of ontology development, from specification to deployment. By using this framework, professionals can systematically build ontologies that enhance data interoperability and enable advanced analytics. In the realm of natural language processing, logic-based knowledge representation plays a crucial role in semantic understanding. By translating natural language into formal logic, systems can perform reasoning tasks such as question answering or dialogue management. For instance, the answer set programming paradigm uses logic programming to solve complex problems by representing them as logic programs and computing their answer sets. ASP has been effectively used in applications ranging from planning in robotics to information extraction in text processing. Incorporating logic-based knowledge representation into AI systems also involves understanding and managing uncertainty. Real-world information is often incomplete or uncertain, posing challenges for purely logical systems. To address this, probabilistic logic frameworks, such as Markov logic networks, combine logic and probability to represent uncertain knowledge. MLNs allow for the encoding of probabilistic relationships between variables, enabling systems to make informed decisions under uncertainty. This approach has been applied in areas such as social network analysis and bioinformatics, where the integration of uncertain data is critical. The practical implementation of logic-based knowledge representation demands a careful consideration of computational complexity. Logic-based systems can become computationally expensive, especially when dealing with large datasets or complex ontologies. To mitigate this, professionals can employ optimization techniques such as heuristic search and parallel processing. For example, in the context of semantic web services, reasoning engines like Pellet optimize the reasoning process to handle large ontologies efficiently. Ensuring the scalability of logic-based systems is essential for their application in enterprise environments. Large organizations often require the integration of vast amounts of data, necessitating scalable solutions. One approach is to use distributed computing frameworks, such as Apache Hadoop, which can process and analyze large datasets across clusters of machines. By combining logic-based representation with distributed computing, organizations can harness the power of AI to derive insights from big data. In conclusion, logic-based knowledge representation offers a structured and interpretable way to encode information for AI systems, facilitating reasoning and decision-making. Through tools like theorem provers, ontologies, and probabilistic logic frameworks, professionals can build robust systems capable of handling complex, uncertain, and large-scale data. By leveraging these tools and frameworks, AI practitioners can address real-world challenges, enhance system interoperability, and improve decision-making processes across various domains.